Okay, welcome back to my class. Now I'm going to discuss about the graphical representation of the zero order reaction. That is, going to construct the zero order flow. Okay, we have the expression, that is a differential rate expression for a zero order as dx by dt is equal to k into ca raised to 0. And the integrated rate expression, that is x is equal to kt or k is equal to x by t. This equation are used for graphical representation. That is, if we use the differential rate expression for the graphical representation, as the equation says, if we plot the rate, that is dx by dt, as the y-axis against the concentration Ca as the x-axis. The equation says that the rate is independent of the concentration of A. So that on plotting the rate versus Ca, we have a straight line parallel to the Ca axis or parallel to the concentration axis. That means there is no change in the rate of the reaction with respect to the concentration Ca or the reactant. So on plotting dx by dt against Ca for a zero order reaction, we have a straight line which remains constant and it is parallel to the Ca axis or x axis. Okay. On the other hand, if we plot the integrated rate expression, that is, it just says that x is equal to kt. That means x is directly proportional to t. That means x is the amount of the product formed. The amount of the product formed is directly proportional to t, so that the rate of formation of the product is a constant. So, if we plot the amount of the product formed in the y-axis against the time t, okay, it means that x increases with the time. That means the rate of formation of the product is a constant with a constant slope. That means it is a straight line, linear line passing through the origin. It is a straight line with a constant slope k passing through the origin. So the graphical representation of the zero order reaction, if you make use of the integrated rate expression, that is x against t is a straight line passing through the origin with a constant slope k. Okay, that is given in this graph. So we have two different graphs here. So next aspect in this connection I have to discuss is in all the kinetics is T half. That is the half-life period T half. The half-life period T half of any reaction is defined as the time taken for the conversion of the half of the initial amount of the reactant. Okay, this the time required for the conversion of the half of the initial amount of the reactant. Okay, that means suppose A0 is the initial concentration of A. When T become T half, that is half-life period, A0 now reduced to A0 by 2. So it is otherwise the time required for reducing the initial amount of the reactant to half of its value. So when we make use of this concept, this is an important quantity in kinetics. So definition of half-life is the time by which the amount of the reactant is reduced to half of its initial value. So when we make use of this, we have the equation that is K is equal to x by t for a zero order reaction. When T become T half, that is, we have taken A0 as the initial concentration of the reactant, and A0 is converted to the product of concentration X, so that if you assume that half of the A0 is converted to X, then what is X? X is equal to A0 by 2. The remaining amount of A0 is represent that X. Now X is equal to A0 by 2. So when T become T half, then X is equal to A0 by 2 according to our definition. So K, rate constant K now become equal to A0 by 2T. The 2T half, okay, A0 by 2T. Okay, that is the time. Okay, now T half. Now T half. Okay. Now T half is okay, that is A0 by 2K. So the half-life period of a zero order reaction T half is equal to A0 by 2K. That is a term that is directly proportional to the initial concentration and inversely proportional to the rate constant. It is an interesting thing that for a zero order reaction the rate is independent of the initial concentration, but the half-life period is a term that is directly proportional to A0. Then another aspect here is at what time a zero order reaction gets completed. At what time a zero order reaction gets completed. Okay, that is when a zero order reaction, we want to know T. At what time a zero order reaction completed. Okay, at the completion, what happened to X? X become equal to A0. That is, all the reactant A0 is now converted to the product X. Now A0 is equal to that is X become equal to A0 at the stage of completion of the reaction. So we have, that is the equation, K is equal to, now X now become A0 at the completion of the reaction, that is A0 by T completion. This is a completion time. So we can write that T, the completion time T is equal to A0 by K. So the time at which a zero order reaction is completed is T is equal to A0 by K. Okay.